Hello, Legacy students. Today we're going to talk about key features of graphs. What you want to have on you, your notes, pen or pencil, color pencils, markers might also help you. Foldable, and then there is also a little scrap of paper I gave you of one of the problems as well for you to write on. Learning targets, tons of them today. So we're going to first look at maximums and minimums. We're going to look at increasing and decreasing. We're going to find x and y intercepts, continuous graphs, bounding, and then also even, odd, or neither. So a lot of stuff is going to be in this video today. The foldable I gave you, you're going to want to cut on the red and fold on the green. And you're also going to want to cut around the edge as well, okay? So there should be no white space around the edges. So go ahead and go do a quick job on that. Go ahead and cut around the edges and then cut on the red, fold on the green. All right, so go ahead and open it up. We have this beautiful graph in the middle. Now we need to talk about some key features of graphs that you would be pointing out throughout the year. So the first thing we want to talk about is the x-intercept. And you guys have found x-intercepts already. An x-intercept is the point where the graph crosses or touches the x-axis. So on my graph, I have a x-intercept at -3, 0, 1, 0, and 5, 0. So those would be 3 x-intercepts that I have marked in. Notice I'm making the x-intercept word purple, made my dots purple as well. So that way you guys can kind of color code here. The other kind of intercept is called a y-intercept. A y-intercept is a point where the graph crosses or touches the y-axis. In this case, this graph only has 1, and it is at 0, 2. Those are not very new. We've played with x-intercepts before. We've played with y-intercepts before. You guys have talked about them also in other classes. The next kind that we're going to talk about is increasing intervals. A function is increasing on an interval if the y value increases as the x value increases. And on this graph, it is right here where we would say that we are increasing. So notice, if you look from left to right, we would say we are increasing on that interval. There is one more interval as well. From there to there, we would also say we're increasing. Now, similar to how we did domain and range, we're going to be using kind of the same interval notation. So for these increasing intervals here, so I'm going to go increasing, okay, we would say we are increasing from -infinity, because that's as far left as we go, right? So I'm starting increasing at -infinity, and then I stop increasing at -1. I'm going to put a parenthesis on that -1, because technically at -1, you're not technically increasing anymore. It's kind of a stagnant area. And then I'm also increasing, so I'm going to put my union saying, hey, I also got a little bit more. It's kind of like an and symbol in our mathematics. I am also increasing from the starting point right here, which is at 3. We're going to always use our x values for it. So I start at 3. And if I move to the right, we keep going up, right? So as I move to the right, I'm going to say I'm going towards infinity for that. The other portion is decreasing. So a function is decreasing on an interval if the y value is decreasing as the x increases. So aka if I move from left to right, I want the graph to look like it's going down. So between those two increasing, I have a decreasing interval. So I'm going to write that down here. So decreasing, I am decreasing from, if I mark that in, starting at -1, right? And I stop decreasing right here at 3, right? Now, this is pretty difficult to figure out and pretty difficult to remember. How I think of increasing and decreasing is if I had a little car going right here. And if this car would be going up the hill, you see how he would be going up the hill? So he's increasing, he's increasing, he's increasing, increasing. Notice right here is when he would start decreasing. So that's where I would have to start or stop my increasing interval. Since I'm going down the hill, and then I'll start going back up. So the car kind of helps you understand which one's increasing and which one's decreasing on it. The other portion, another thing we want to talk about, is the maximum. The maximum of a graph is the y value of the highest point in a particular region of a graph. One might call these the mountain of a graph, okay? They're going to look like a mountain. In this case, my maximum is -1, 4. It's the order pair -1, 4. Second part of this is the minimum. The minimum is the y value of the lowest point in the particular region of a graph. This would be considered your valley of your graph, okay? So in my case, my value of this graph is at 3, -4. That would be my minimum of this graph. Now, there's other words you might hear thrown out about the x value whose graph corresponds to a y value of 0, aka your x-intercepts. These are your zeros, your roots, your solutions, and intercepts. All of these are the same word for your x-intercepts, okay? So keep that in mind. As you're finding these, you might, let's say you're taking the ACT, they would say, what's the zeros of this graph? All they're saying is what's the x-intercepts. So be very careful, just kind of knowing the different lingo that someone might use will assist you definitely as you're working through. Some other features that we want to talk about that you're going to want to write in your notebook because consistently this is going to be happening. Continuous is one kind of thing. Graphically speaking, a function is continuous at a point if the graph does not come apart at that point. So right here is a graph that's continuous at all x. The best way to tell what is a continuous graph is ultimately if I start at one end of the graph and I can draw the entire graph without picking up my pencil, I would say it's continuous, okay? So basically continuous means is if I start at one end, can I draw the entire graph without picking up my pencil? A majority of graphs are continuous, but there are a couple that we'll be looking at in this class specifically, and as you continue in your math career, that are not continuous. So we're going to make sure we kind of know that word now so that when it comes later in your math career, you know the word and recognize it. The other key feature that we're going to want to talk about is boundedness. So a boundedness is just that there's a maximum or a minimum that exists, called an upper or lower bound. And there's a couple of different things that could be happening. You could have a function that's not bounded. That would mean it doesn't have a max or min. You could be bounded below, which the word for the fancy definition, a function f is bounded below if there is some number b that is less than or equal to every number in the range of f. That number b is called the lower bound of f. Okay, that's really fancy words for there is a min. Okay, there's a minimum and it's the lowest minimum that the graph can get down to. Okay, bounded above is a function f is bounded above if there is some number b that is greater than or equal to every number in the range of f. Any such number b is called the upper bound of f. This is there's a maximum. And it's a tall maximum. It's as tall as everyone else. So you're just kind of keeping that idea in that regard. Bounded function is if you're bounded above and below. So that would mean there's a max and a min. Now, these are kind of confusing to read. Okay, so let's take a look at the actual pictures of this, and this is probably going to make a little bit more sense for you. So here's a visual look at bounding. This function in particular is bounded below because this graph is going to continually stay along the y-axis. It can't pass that point, okay? Bounded above would mean looking at my graph here, notice how it's not going above this line. That's how I would say it's bounded above. Not bounded means there's no hills and there's no valleys. So like right here, this guy's not bounded because he goes forever this way, forever that way. I cannot say he's bounded in any shape or form. Then you got another graph that has hills and valleys. That would be bounded. He's stuck between two sections. So that's what we're kind of thinking about in that. Some other features of graphs. Extrema is another word you might hear thrown out. An extrema is a local or relative max. That's a high point on a certain interval of the graph. Now, a graph can have more than one local minimum or maximum. It doesn't really matter, but there is only one absolute maximum, okay? An absolute maximum is the highest point on the whole graph. This would be the highest hill. Highest mountain, okay? These would be all the other mountains that are on there. You can also have a local minimum. That is a low point on a certain interval of the graph. So these would be your valleys. Okay? But these, you can also have an absolute minimum. That is the lowest valley. So when you're looking at a graph, you're going to be looking for where are all the valleys and then what's the lowest valley. Now, sometimes you don't have these. Sometimes you just don't have a max or a min, and that's okay because they actually have to be an actual hill or an actual valley. They have to, by definition, start increasing and then decreasing. That would be a maximum, or decreasing, increasing for being a minimum. Other features of graphs, even, odd, or neither. Yes, you did this already, so this should not be new, but reviewing the information. Even remembers that you're symmetric about the y-axis, so that means I can fold it in half. Odd is symmetric about the origin. Now remember how that looked. We folded over y and then over x. So we folded over the x-axis and the y-axis, and that's how we knew that we were an odd function. And then you also have what's known as a neither function, which is just neither symmetry. So you want to find that little graph in your notebook that I gave you or in the pile of papers to be able to complete this information. I'll wait a quick minute so you guys can find that. Okay, since you have found that little piece of paper, let's talk through this problem. So, first thing they want us to find is the x-intercepts. So remember, that is where you cross the x-axis. So, I got one right here, one right there, one right there, and one right there, right? So let's write their ordered pairs. So my x-intercepts are at -4, 0. It looks like I got another one at -3, 0, right? This guy, he's kind of off in the middle. So let's say he's at, I'm going to say 1/2, 0. And then I got the next guy at 3, 0. Okay, so we're looking through these ones. Y-intercept is the opposite of x-intercept. It's where it's crossing the y-axis. Usually there's only one y-intercept, but there could be multiple depending if it's a function or not. So right here is my y-intercept, and it looks like it's at 0, -2. Now, these should always be written as ordered pairs, okay? So always write those as an ordered pair as you're writing your stuff. Looking at this graph, is it even, odd, or neither? So remember, even folds along the y-axis. So I'm looking at this guy, definitely not even, right? He's not going to fold perfectly. Odd means that if I fold it over the y and then fold it over the x, it should line up. Definitely not, right? So this guy is neither. Continuous. Continuous means is if I start on the left-hand side of my graph and I start drawing, can I draw the entire graph without picking up my pencil? So I'm going to do that. Not picking up my pencil, not picking up my pencil. Definitely continuous, right? Because I could draw this entire thing. So I would say, yas, it is totally continuous. Yas. Okay. How is this guy bounded? Remember, is it bounded below? Is it bounded above? Is it bounded at all? Or maybe it's not even bounded. So in this case, looking at it, it's definitely not bounded below, right? Because there is actual arrows, so I can't put a line down here and my graph doesn't go past that line because those arrows are just going to bust through that line. But if you notice right here, I'm not going above that line, that dotted line that I just drew in, right? So I would say that this graph is bounded above because there is a line I can draw that the graph does not cross that line. That's all bounded is asking is, Do you have a graph that's going too far up or too far down? Okay. Increasing intervals. Again, this one's kind of different. I'm going to think about my little car here. Beep, beep. Okay. I know I should have been an artist one day. Noticing if I start driving, right, I'm going to be going up the hill. So I'm increasing. So I'm starting at negative infinity because we're thinking the x value. Do not think the y, think the x. So I'm starting at negative infinity. And I'm going to keep driving, keep driving, keep driving, keep driving, keep driving, keep driving. Oh, I'm going to go over a hill, right? So right here, we started to go down. I stopped going up the hill and started going down. So that x value that I just drew, that looks like negative 3.5, right? So I'm going to say from negative infinity to negative 3.5, I was going up a hill. Then noticing at negative 3.5, I'm starting to go down a hill now, right? So I'm decreasing from negative 3.5 to, let's figure that out. So I'm going to go down the hill, down the hill, down the hill, down the hill. Oh, I hit the bottom, right? So right here, roughly, is me hitting the bottom of that hill. Well, that's probably like negative 1.5, right? And I'm kind of rounding, I'm guessing. You don't have to make them perfect. So this is negative 1.5. That's where I'm stopped my decreasing. Notice we're going up the hill again. So I'm going to put a union, basically an and. I'm also increasing from negative 1.5 to, let's figure out. So again, my car, if I drew my little car here, he's going to be going up the hill. Right here is when he stops going up the hill, right? So we're going to kind of draw that in. Notice that's at 2. So from negative 1.5 to 2, he was going up a hill. And then he's going to go down the hill forever, right? And since he's going down the hill forever to the right, I would say from 2 to infinity, he is decreasing forever. Okay? Increasing and decreasing is probably one of the hardest things for kids to get past. But once you get it, it just unlocks and you're just like, yes, I could do this forever. Okay? So just keep working on it. If it struggles, trust me, I can help you with as many problems as you need. Now, let's talk about maxes and mins. I got to do some erasing here because my graph's kind of getting all fuzzy. Okay, there we go. We'll leave my car down at the bottom for my masterpiece. So, maxes are the hills. Notice, we got 2 of them, right? I got a hill here and a hill here. Now, the maximum, so we have a maximum at, looks like about negative 3.5, comma, 1, right? Then I have another max at 2,5, it looks like. I'm going to do some scribbles here. These are my maxes. Okay. And then I have one at 2,5. Now, I want to identify which one's the absolutes and which one's the locals. Now, absolute is the tippy top. He's the tallest. He's the Mount Everest of my group. So that would be this guy, right? Because he's the tallest mountain. So I would say 2,5 is the absolute max. This guy right here, he would be a local max. He's not as tall as Mount Everest. However, he's still a maximum, right? He's still a hill in the mountain range. So I got to notate that he's there. Minimums then, let's look here. This guy would be a minimum right there. And his ordered pair, kind of disgusting, right? Negative 1.5 and negative 5.5 maybe. Okay. Now, is this an absolute or a local minimum? Well, it's not as far down as the graph goes forever, right? Notice this graph's going down forever. So this guy is not technically an absolute minimum. This guy would be a local min. He is not the lowest the graph can be, so I would call him a local minimum on my graph. This graph in particular does not have an absolute minimum. Okay. Now, domain. We've already practiced this. This is not new content, but nevertheless, well, how far left can this graph go? Well, this graph's going to keep opening up left, right? So we're going to say it starts at negative infinity. And how far right does it go? Well, it keeps opening up, right? So he's definitely going to infinity. So his domain is from negative infinity to infinity, taking a look at its range. So starting bottom to top, right? So it goes forever in the downwards way. So we're going to say it's negative infinity. But how far up does it go? Well, right here, right? This is the highest point of the entire graph, which is 2, 5. So I would say his range, the highest y value I get to, is 5. And yes, I did hit that 5. So there would be a bracket on that 5. That's the end of the video. I know it was long. Trust me, we're going to get tons of practice on this as we continue. So, I will see you later, Sabers.